Recording in progress.
Let's start. Yeah.
Like introduce it? Sure. Yeah. Okay. All right, yeah, thanks everyone for coming. Today we have Ayush, who's also one of the organizers of the seminar. He's going to be talking about using LLMs for research level inequalities.
All right. Hi, my name is Ayush, and thanks for attending my talk today. I'm a postdoc at Rutgers, and I've also been working on creating tools that can be helpful to math researchers like myself. So before I start, I'd just like to motivate sort of how I see these tools. My sort of day job is proving research level math, is solving research level math problems. So there are really two kinds of AI tools or any tools that are useful to mathematicians. One is just sort of using a very powerful AI tool like a big hammer and just using it to solve a hard problem. And the second is sort of more fundamental research in which you play around with these smaller models and then you tweak things and then you see whether you can improve performance based on like things you change about the model. So I don't necessarily care about the second, right? There are problems that I'm stuck on. I want to use a big hammer. I want to use the best model available there and just solve the problem that I'm stuck on. All right, so that's the perspective that I have towards these tools. Right, so can these AI models sort of help me get a fresh perspective on the problem so that I can just use those insights to solve the problems, right? And all of this is joint work with Vijay Ganesh at Georgia Tech. All right, so that's the so there are three parts to this: the motivation, which is what I just told you, the implementation, in which I explain how we sort of create this pipeline that with a frontier LLM and a computer algebra system to sort of take a difficult problem and break it up into tiny pieces. And then for each of those pieces, like a computer algebra system proves each piece so that put together, you have a proof or you have a verification of a conjecture. And then drawbacks, I'm going to be very pointed about the drawbacks because we are all mathematicians and computer scientists. We want to get to the bottom of it, like how useful this is and how do you assess how useful the tool is. Okay, so so AI tools for math, there are generalist tools that can solve hard problems. So, like larger, more powerful models with better verifiers, better tool calls can sometimes help you in your research, right? For example, ChatGPT 5 Pro, which is sort of the most expensive version of ChatGPT, has been pretty useful for mathematicians in the recent past to sort of be able to solve some problems in problems that are more amenable to tools like these, like problems in optimization, maybe some combinatorics and things like that. Right. So recently, these tools have been becoming more and more powerful, and they can actually help math researchers in their work in some areas. Like some tools, like for example, I'm a differential geometer. So in my field, sort of things are not as helpful yet, but in some places like optimization, they can be pretty helpful. And then there are specialized tools that target universal pain points, right? And these pain points are difficult to know unless you are a mathematician. Like sometimes you know how to prove something, or sometimes you know something should be true, but it's going to take you 45 minutes to write everything down and confirm that your intuition is correct. So can you just take a tool, plug a formula in or plug a question in, and get a true or false result, right? That tells you, okay, you're on the right track. You have the details, and now you'll just flesh them out in your paper. So you don't spend 45 minutes verifying whether this thing which should be true is maybe false. Maybe you just get a false result, and then you should tweak the constants or something. Right. So most AI companies have been targeting the first kind of questions, which is sort of can you solve like a big millennium problem, or can you get a gold in the IMO, or solve these really hard problems that people struggle with, or but very few companies are sort of targeting the second kind, which is can you reduce my busy work by 45 minutes so that I can think about the ideas instead of writing down some calculations I know how to do, right? So because we're mathematicians and computer scientists, we care about both. So the tool that I'm going to be talking about today essentially does the second kind of thing, which is that ideally it can sort of cut down on my busy work so that I can sort of think about the big ideas, but it should really also be able to do the first. Because we have a big hammer and we can use it anywhere you like. Right. So I'm going to sort of explain how this is happening. Okay. All right. Some background on this problem. I run a research group with some undergraduate students at Rutgers. They're very, very good. And they were able to generalize a technology by Google DeepMind last year. So they were able to generalize fun search to something that they call Darwin. I think they also have GitHub code for that. I was very proud of them. So I sort of put up a question on Math Overflow under a false name because it sort of allows you to ask stupider questions on the internet. And then I said, well, I have some students, I'm very proud of them. What other problems can they attack using the technology that they've developed? And so Terence Tao answered, surprisingly, and he said, well, here's this complicated looking inequality. Can you solve it using a tool like alpha geometry? Right? So for example, alpha geometry is, as you might know, is a technology that was developed by Google DeepMind, and it is able to prove problems in plane geometry at the IMO level, right? Which is very impressive. So the fact that an LLM can do that, and there's a sort of two components to it. They have an LLM, and then they have a verifier, or something that produces a proof. And so potentially this pipeline of taking an LLM and then taking something that can produce a proof, it's pretty general. It's not restricted to plane geometry at the IMO level, right? You should be able to use it anywhere. So can you take a pipeline like that and use it to solve or prove complicated inequalities like this? So of course, I've talked to Alex about it, is that this inequality is not difficult or pretty evident to experts in, say, number theory or areas like that. But it looks like very complicated to me because I have, maybe I have to think about it and maybe have some experience with some series like that to know what to do, right? But can you create a tool using alpha geometry or an idea like that can prove these inequalities? Okay. And then okay, so what exactly does this notation mean? So I read on Wikipedia that this is just, it's called Vinogradov notation. Maybe you have the pronunciation wrong, but it's just a big O estimate. So can you prove that A is of order B? That's all that means. So can you prove big O estimates using an AI tool? And not just numerical verification or numerical or calculations that support your conjecture, but actually prove it. So it should be able to return either a proof or a verification saying, true, this is correct, I have proved it.
The mathematical physics that means a bit low.
Is that what it means?
But no, they're wrong. This is because of Knuth. Knuth just decided to take Vinogradov notation, which comes with number theory, and change it and ruin it, and now there's ambiguity about what it means.
Okay, so I'll just maybe spell out the definition on the next slide to tell you exactly what it means. It means, this notation means there exists a positive constant C such that at every point in the domain, F is less than or equal to that constant times G. All right, that's all that means. So which means, can you produce a positive constant such that F is less than or equal to that constant times G? Okay.
Really, it should be asymptotic notation. So in a filter, there should be big O. So it's not for every point in the domain, but eventually.
Right.
But whatever.
Right, but based on the overflow post, okay, so maybe this means something similar, but not exactly the same. But this is the definition that I'll be talking about. But you're quite right. Maybe there's an asymptotic component to it. But I'll be talking about this one, which is at every point in the domain and not just eventually, you have this inequality. Okay. And okay, so like any other PhD student or postdoc, I thought this was interesting. I'm definitely going to work on it, and then I forgot about it, right? So then, I sort of waited a few months. I looked at how they trained alpha geometry. It seemed too complicated. I thought maybe if I learn more about how to train these models, I'll eventually get there and I'll be able to train a model, how Google DeepMind did it. I talked to a few ML researchers. They told me it's going to cost you a lot of money. I dropped it, right? So I was like, okay, maybe eventually someone will do it. It's probably not going to be me. All right. And then a few months passed, and then you sort of see this blog post by Terry Tao, who was trying to do the same thing by himself, right? So he's like, all right, so I told some guy on the internet to do this, he's not going to do it. So let's try and do this. It seems important enough. So, and then you sort of, then you sort of realize that, all right, this is pretty important. Maybe you should try and do it. And then there was also like a public repo, which was created. I think until 3 months back, there was some like contribution from a bunch of people, but the idea was to sort of do it as a community and develop this tool that can improve these inequalities. And I'm going to talk about how our approach is different from that and more powerful than that.
So you said that Khaitan developed the tool or said that it was important to develop the tool?
He said it was important and that he was going to try and develop it. But he was using a completely different approach. That in some sense is under par to prove anything like this. Right. Okay. So what are possible methods that you can use to develop a tool that can prove big O estimates, or at least my definition of those estimates, which is given any two functions, f and g, you prove something like this, which is that something like this, which says that there exists a positive constant such that f is less than or equal to c times g. Now just to sort of give you some motivation, there is nothing special about this. Our tool can prove inequalities in general. It doesn't necessarily have to be, this notation. It can just sort of, well, certain kinds of inequalities, but it is powerful enough to be able to prove that if you have a conjectured inequality like this, and you're not quite sure whether it's true or not, you can ideally plug it in. And then if it returns true, then you know it's true. Okay.
Part of theta 0 is less than.
Right. Haven't tested that yet. Right. But that's something that I'll spell out, which is the limitations, which is what do people really mean when they say they have saturated a benchmark, or when they've, like saturated, say, mini F2F or something like that. Like, because at Rutgers, we want to be very, very sort of precise to what that means. And this sort of doing a project like this makes you a little depressed that it's not really, it's things are very different from what they appear. Okay, because almost by design, you kind of have to hard code a lot of these things yourself, and you can only hard code a limited number of things because you have limited amount of time. And so, you sort of, I'm going to talk about it in a bit. Okay.
You're just saying that the benchmarks that exist for evaluating LLMs on how they do on math are not very useful for actual math.
Yes. Yes.
I would love to see that, because that's exactly the feeling I have, but I don't have a quantified way of saying that. Maybe you do.
I'm glad you brought it up because I'm going to talk about it right now. Yes. All right. So, okay, alpha geometry. Now, at first we tried to use alpha geometry, which was an alpha geometry type approach. Okay, what does that mean? Okay, so last year, maybe 2 years back, 2023, Google DeepMind released this tool. It said it has created this tool called alpha geometry, which can solve IMO level plane geometry problems. All right, like a lot of math students, I prepared for the IMO, and like most of those people, I did terribly at it. All right, so I was extremely, extremely impressed that you now have an AI tool that can prove IMO 2010 problem 2 in 7 seconds. Like that to me is incredible. And if it can do that, then it should be able to solve a simple undergraduate level problem or a PhD level problem given enough context. So for example, if it has a very, very strong logical ability, then if I give it enough definitions or give it enough theorems, or maybe have it access those definitions and theorems on the internet, whatever, you can have any combination of these things. It should be able to prove some simple things, or maybe at least attempt to prove those simple things, right? So I sort of started this undergraduate research group in which we try to do exactly that, which is sort of, take alpha geometry, maybe implement it, and then see if you can modify it in some sense. Okay.
You succeeded with fun search just from the description of how fun search is supposed to work.
Right.
You could reverse engineer.
No, the fun search, both of these code bases are public.
Ah, so you literally can take fun search and then adapt it to your
That's correct.
setting, and similarly with alpha geometry, it's public.
That's correct. Alpha geometry.
Take the code.
Yes.
Not the model that it's run on, or the model.
The model.
Everything about alpha geometry is open source.
Yes.
Amazing.
Yeah, we've run it. I've run it on my laptop.
Wow.
Yeah. So both of these things are open source. I know alpha geometry 2 is not, but alpha geometry 1 is open source.
Okay.
Runs on a laptop. No, you can download it and run it locally.
GPU on the laptop?
Sorry?
On a GPU on the laptop?
No, just on my laptop without a GPU. 8 cores, yeah, a MacBook, yeah. Yeah. With a caveat that Okay, I'll tell you about the caveat. The LLM is, the associated LLM with alpha geometry is not that useful. So you can completely disregard it and make API calls to like a different LLM. And as long as you do that, you can sort of get the same kind of results. But you can do that.
So it is making API calls from within alpha geometry. But you can't,
Without internet, you can't run.
without internet. Does it run or not?
I think I did manage to run it on my laptop without the internet. The version that worked most smoothly was with the internet when I was making API calls to a different LLM,
Not to Gemini.
not to Gemini.
To what were you?
Maybe I was using, I think it was Gemini actually, now that I think about it. I don't quite remember the LLM, but what I remember is that the LLM associated with alpha geometry was not that important to sort of have you can make an API call to a different LLM that wasn't specifically fine-tuned for that task, and it still did pretty okay. Yeah. But it doesn't matter what the LLM is. It doesn't even have to be as good as Gemini. It can be something much smaller, which was 2 years back, and you can still make it work. Okay.
But alpha geometry was never designed to be general purpose. It was specifically for a geometry problem.
That is correct.
But you're gonna apply it to inequalities.
I'm not going to apply it to inequality. I'm going to tell you, yeah. But the idea of alpha geometry is sort of
The way it was trained, if I understood correctly.
right, or at least it's been the way it's been implemented. Exactly, yeah. Okay, so how does alpha geometry work? So I'm going to give a very silly example, which is if you're trying to prove Pythagoras' theorem, which means, if you're given a right angle triangle, you're trying to prove a squared plus b squared equals c squared. Now, I think there's 500 proofs or something like that of Pythagoras' theorem, but in none of them can you just look at the diagram and prove it. You have to make an extra construction, right? One of those proofs is that you make a perpendicular from one point to the hypotenuse, and then you can sort of use something like this triangle, and then this triangle, and then the big triangle. All of these three are similar. And then you can make inferences about the ratios of the edges and then do some calculation and you get Pythagoras' theorem. There's other proofs as well, but all of them require at least one additional construction. Right. Now, the additional construction is the creative or the difficult part, which means out of all possible, like 100 things or maybe more, you can construct the circumcircle, you can construct this side, you can construct the incircle, you can take the intersection of the whatever. You can there's a bunch of possibilities really, and you have to choose the right one, and that comes from experience, right? So it's for that you use an LLM. So the LLM suggests what's the construction you should make. And once you make that construction, now there's computations which you can hard code, which means compute everything, compute all the sides, compute all the angles, etc., and see if you've reached the goal, right? If you've not reached the goal, make another construction. So make another API call to the LLM, or make the LLM make another guess as to what's the next construction, right? And so on. And within in a general problem like that at the high school level, maybe you make 2 or 3 constructions and then you reach the goal or something like that, right?
For IMO level problems, that few constructions, few creative steps to computation.
So for like problem 6 or something, which is like the much more difficult ones, you need maybe 3 or 4 jumps. So maybe 3 or 4 constructions, something like that. But the number of inference jumps or the number of creative steps you need decreases with if the difficulty decreases. So in some sense, problem 1 might be 1 or 2 constructions, but then problem 6 might be 3 or 4
But
constructions.
instead of some massive tree that you would have to search for all possible things you could construct at any particular
Right,
location, especially if you're chaining 3 levels of this.
right.
Instead of that, you're just calling an LLM.
Exactly. So instead of exploring the tree of all possible constructions you can make, you just make an LLM and say, what do you think is the most probable next construction that will lead me to a proof?
So how big is the tree that it ends up searching?
So I don't think the LLM, okay. I don't know how an LLM works, yeah. But it's sort of, yeah.
But the LLM only gives you one suggestion.
Yes.
And then you go into compute from that.
That's
You
correct.
still haven't done it. You either go to another depth or you say, no, never mind, we'll go back. Like, how do you evaluate?
Yeah,
There
so
has to be some kind of evaluation function of how you're gonna explore the tree.
right. So I mean, suppose a silly example is you're given a very specific geometry diagram and you're asked to prove that a certain side is equal to 1. You almost never get that in an IMO problem, but let's suppose you're trying to prove that a certain side is 1. Now, you ask the LLM, what's the construction I should make? And then it makes a construction, and then you calculate all the sides. And then you see, can you prove B is equal to 1? Have you reached that goal yet? And then it says no. Then you go back to the LLM, now make another construction, how to do that. And then it sort of constructs something else, and then you again make all the computations.
And are you remembering what you sent to the LLMs of the history of?
Yes. Yes, so you're sending the current state, which is that,
Context window keeps growing, even your failed attempts, you send it,
yes,
I'm just curious.
yes,
Way to shrink the size of the search space.
Yeah.
So, for example, you can start sampling possible histories, right? So let's say for each search, previous step, you search like 1,000 first try, right? Maybe only a few of them is correct. The next time, you can start something like a 10 history.
How do you tell what's correct?
No, you don't need to. You just random is the next layer. Let's say you shrink it to be 500, and each of the LLM can look at like a 10 random first layers result with the like computation feedback, right? And can use that to further like consolidate and propose the next one. If you have this natural way of shrinking without knowing the answer, but in the end you reach something. That should be the right answer.
You're about to tell us that this didn't work, so.
Yeah.
We should stop asking about it.
no, that's fine, that's fine. No, this is important because this sort of tells us that, okay, we have this complicated sort of machine, it can do very impressive things. And, all right, so for the creative step, DeepMind trained an LLM from scratch. So this is the main point, which is that they did something that's very expensive. That's how they trained AlphaGo, which can play Go and, perhaps better than humans. And, they did that for chess as well. And for proof generation, they sort of hard-coded all possible proof strategies that one could use to prove facts in plane geometry. The surprising thing is, we could not even make alpha geometry prove Pythagoras' theorem. Pythagoras' theorem.
Yeah, you understand you've got this comprehensive knowledge base
Yes,
of all strategies, and it couldn't prove.
it couldn't prove Pythagoras' theorem. Yes, it can prove all of these it had like a 72 or 77% success rate on IMO geometry problems. It should have been able to prove Pythagoras' theorem with its eyes closed, but it cannot prove. Yes, so, like, don't buy the hype. A lot of these tools, or maybe we went about it the right way, but we, not for lack of trying. We tried a lot. We tried to ask it the same questions in many different ways.
Try making squares on the sides and asking if the areas add up.
No, we didn't try that. But
That's Pythagoras.
sure,
Are any of its constructions reasonable?
it just says proof not reached. So it would sort of,
Can't see like the intermediate creative steps I was trying to make.
I don't think so. It just outputs a proof object at the end.
You can try another Gemini version.
Sure, yeah. I mean, like Gemini can of course prove Pythagoras' theorem, but alpha geometry, which is this extremely impressive geometry tool, it's completely possible. We didn't, there's a way of asking this question, which can make it prove that's entirely possible. But we just asked it the plain sort of hard sort of way to prove,
It should be able to do it.
it should be able to do it. Yes,
On your local install, did you manage to solve the IMO problem?
Yes.
Well,
yes, yes.
Okay.
So, because we mathematicians, we actually care whether these tools are useful to us and not just that they claim to solve some difficult problems. A lot of these tools are not always what they claim that they are. Okay.
Wow.
So, this is not secret knowledge. This is sort of, this is just what my experience with LLMs, trying to make them solve my research problems is as well. Just
We should get JJ to come and tell us about alpha geometry.
sure. Is he at, close? Okay, right.
Yeah, exactly.
Right. Right. Okay. Do we need to spend hundreds of thousands of dollars training LLMs this way? So one of the most important talks of my life that I've ever attended was last semester when we had a researcher from Alpha Proof from DeepMind. You attended that as well over Zoom, in which he talked about, we had a talk in this seminar in which he talked about how they trained Alpha Proof, which is sort of a more general tool that can solve all kinds of IMO problems and not just geometry.
So come on, Aubert.
Yes, Uber, yes. And he sort of said, all of this alpha stuff you don't really need. Just take a large LLM and do reinforcement learning, right? So whatever gains you have from spending $100,000 by taking these GPUs and training things from scratch, you don't necessarily need that because you're losing out a lot of context that's there on the internet or that are there in the data sets. So perhaps it's inefficient or whatever, but you can just take a large model off the shelf maybe do some reinforcement learning on IMO problems, and you have something that is far more impressive in that it can not just solve plane geometry problems, it can solve all kinds of contest math problems or difficult problems that that are not advanced, but there's still some like trick that you have to use that you have to discover to solve them.
There's a lot of math problems that you can always map to plane geometry problems.
Yeah, I'm sure there are. Yeah,
That beyond, things that may not look like a traditional plane geometry problem.
sure.
Just look at the graph of it.
Right.
But Alpha Zero, which was trained on IMO problems, high school level problems, was able to close a whole bunch of goals in the prime number, doing complex analysis that it had never in its life seen. So
Right.
I think the generalizability is much more than just problems can be reduced to geometry.
Exactly. So this is just the same lesson, which is that bigger models are better. Smaller models in general have just hard-coded solutions to specific problems on a benchmark, or at least, it's true for a lot of things out there. So, it's just sort of the bitter pill again and again, which is that you need a model that can get context, that can generalize. And for that, a bigger model is always better. So if you're trying to solve, if you're trying to sort of do research with AI, et cetera, but if that is not your primary goal, if your primary goal is to solve a different problem that you're stuck on, using a bigger model always gives you better returns. So this is what they had with Alpha Proof as well. And this is what we're going to use in our tool as well, which is that to train a tool like this, you just need, make API calls to Gemini or ChatGPT-5 or whatever, as long as it's not too expensive. And that's almost always going to give you a better result on problems that it has not seen. Right. Okay. Okay. And how to reliably generalize this to problems outside of plane geometry. So I was talking to a researcher at UT Austin, and actually his student who works in AI and math. And he told me that the reason why alpha geometry became such a big thing and became a Nature paper and so on is not because it's impressive, which it is, but that it chose the right problem, which is that you can take any plane geometry problem and there's 25 things to try. And those 25 things almost always give you the proof, right? But if you take something like algebra, in which the space of possible manipulations is much larger, and you have to hard code them like it was in alpha geometry, it's a much bigger task. So algebra is not as amenable to an alpha geometry type thing as plane geometry is. So it was the choice of problem that really made it such an impressive tool. But for a different choice of problem, maybe that's not always the right approach.
Okay. Saying that papers published in Nature are necessarily good.
Right. In fact, I'm saying the opposite. Right. Anyway, so that was like our lesson, which was that the technology is just out there. You can do much simpler things, and they're probably going to work better. And okay, so this was the approach that Tao and his collaborators were taking, which was lean tactics. So you can sort of you have you have like tactics like say SIMP, and I think there's like fancier ones since then like ESIP, etc., which can sort of try many things at once and see if they can close if they can complete the proof. But they're very underpowered yet to sort of be able to prove something non-trivial, like say the Cauchy-Schwarz theorem. I mean, of course, it's probably a theorem somewhere, but if you take like a non-trivial contest inequality, ESIP or SIMP are not gonna close the goal. Right. So lean tactics are in many ways the right way to go about it, because they give you a proof object, right? You can take that proof and then you can externally verify it whether it's correct or not. But this requires much more programming than I sort of have experience with, in that you have to create this very massive tactic. There's a lot of research that goes on in creating powerful tactics, and we're not there yet. That you can just take, it's like a very, very powerful lean tactic and be able to complete the proofs for non-trivial things. Okay, and Tao also tried, if you look at the GitHub repo, which is sort of public, he also tried, SymPy, et cetera, but then those sort of don't always work very well. Yeah, which is, so after like a lot of programming, you can prove something like this, which is that if, this is true, then this is true, then you can add them or do some other kind of simple manipulation and you get this, which is very different from the kind of problem we saw at first.
That's linear.
Yeah, that's linear, yeah. Yes. So you can sort of take an input, you can simplify it using SymPy and then feed it to lean, and then use something like linearith, and then that can prove things like this. But you can't prove more complicated things, or much more complicated things than that. Okay, so here's our workflow. I'm going to talk about the drawbacks in a bit, but this is the basic idea. So Tao in his sort of math over full post and on his blog post sort of said that many of these inequalities, suppose you're trying to prove that f is less than equal to g, and you're trying to prove it on a domain, which I've sort of drawn here as it's like R2 or something, then sometimes these proofs are simplified by dividing the domain into smaller parts. So maybe a proof for this right now would be non-trivial because you sort of you don't see an algebraic way to prove it right away. But if you divide the domain into two parts, then the proof here becomes trivial and here becomes trivial. And what does trivial mean? An automated theorem prover can prove it, right? So can you somehow simplify the problem enough so that an automated theorem prover can prove it? And simplifying here means, can you break up the domain into smaller parts such that within those subdomains, the automated theorem prover is able to complete a proof?
Almost all of analysis is epsilon over 2 plus epsilon over 2 is epsilon.
Right. Exactly. Right. And this is a pretty sort of universal tactic, which is just divide the domain, and then within those subdomains, things just become substantially easier. And I'll give you sort of a very silly example.
The choice of domain, okay, so that you'll get from an LLM.
The choice of domain isn't the subdomains, yes, that we'll get from an LLM, yes. So the workflow is, so what we initially did was that we sort of created a GitHub repo, and we were like, all right, so mathematicians are going to download it, and then they're going to use this, they're going to run code on the command line, and they're going to get the output. And we were told, no, don't do that. Create a website where mathematicians can click a button and get the result. They shouldn't have to download GitHub. They shouldn't have to download VS Code. They shouldn't have to even download Mathematica or any software. They should be able to click a button and get the output. So that took much more time. Right. Right. This is just for like wider adoption, which is that, for example, until a year back, I didn't know how to use GitHub or VS Code or any of that. And it took me a long time to learn it. And you shouldn't have to learn it. I mean, of course, you can choose to, but if you want to use a tool, you shouldn't be forced to do that. For example, even for alpha geometry, it was extremely difficult to just install everything on my computer and make everything run. I was using Claude all the time. I didn't really understand the code base. I didn't quite know how to make, it's very complicated, and I don't think research groups make it particularly easy to use their tools. But this is an underappreciated aspect of this, which is that if I don't know any programming, I should still be able to use it. And so we created a website and everything that I'm going to talk about in a bit. Okay, so the idea is a user should be able to put in their conjecture in LaTeX, and we in fact changed it to that they can also put it in natural language. Right, so you can put it in whatever format you want, and of course we make an API call to convert it into the right format, and then you pass it to Gemini, which tells you how to decompose the domain. So the most difficult and creative part of it, we just let a big frontier model do it, right? And once the domain is divided into the right subdomains, then you ask Mathematica whether it can prove the inequality in those subdomains. Now, Mathematica is generally used for numerical computations and not proofs. But Mathematica does have something called resolve, which can produce proofs using just first order logic. So when it returns a Boolean value like true, it has produced a correct proof under the hood, but because it's closed source, it doesn't return a proof object. It only returns true or false, true or not proved, right? So I'll talk about why we use Mathematica instead of, say, an SMT solver or Sage or any of these other automated theorem proofs in bit, but Mathematica was the best tool that we found. Okay, it's much more powerful. Yeah.
Without like feedback, it doesn't.
Yeah, if it doesn't prove, then you can, of course, it goes back in a loop, and then the LLM is told that proof not completed. Can you try a different decomposition?
If Gemini can do the creative part, why doesn't it just call Mathematica for you?
And why didn't you do it in ChatGPT where you could call from Alpha?
Right. So the reason why we didn't do that is because there is a lot of Mathematica code that we actually have to put in to simplify the expressions until resolve is able to complete the proof. So this is not, we're not just taking the output from Gemini and putting it into Mathematica. There's like 2 pages of simplifications that the algebraic expression you're putting in undergoes. We essentially extract the leading order term. For example, for a series like this, even if you give it the right decompositions, resolve is not going to be able to complete the proof. So you have to simplify it and run some integral tests, etc., until it's so simple that something like Mathematica's resolve function is able to complete the proof. So even though I say it's the most powerful tool out there, it's still not really that powerful as a human mathematician is. So you really have to simplify it a lot. And there's a lot of mathematical sort of domain knowledge that goes into how to simplify it, etc., that goes into it before Mathematica is able to complete a proof. Okay. So there, you're quite right. So you could ask an LLM to do that, but then we have an intermediate stage where we write a lot of LLM, a lot of Mathematica code that is also passed to Mathematica Cloud as an API, in the API call, and then Mathematica uses that code to process the input and hopefully complete a proof.
I guess you have a prompt so that what comes back from the LLM is exactly in the format that you need to
Yes.
send it on to the next step.
That's correct. That's correct. So for example, we have, like the Mathematica code is like, there's like Python code in between. So you have to create an instance of a certain Python class. So for example, if you say prove that x squared is greater than or equal to x, if x is greater than or equal to 1, then the correct format is that, LHS is equal to x squared, RHS is equal to x, and then the domain is x greater than or equal to 1, etc. So then you sort of have to process it. And because there's a lot of variability in which humans might put that input, you sort of need an API call. We tried using like regex or other things that can sort of extract the expressions from the input, but there's so much variability that you just want to use an API call. And it's able to create the right kind of instance for further inference. Okay, so this is what the website looks like. There are some examples on the left-hand side. You can just click this and it's going to solve this problem. And then of course you can put in your own problems here as well, but you can just test whether the tool works. And below this, it sort of gives true or something. And which means that Mathematica has been able to produce a proof for your desired conjectured inequality.
But sorry, if Mathematica only says true but doesn't tell you why it's true, and you're trying to use this because you want to save yourself 45 minutes of
Right.
it.
That's a fair point. So the ultimate goal is to have a lean tactic that's so strong that it's able to actually save you those 45 minutes. But right now, it sort of saves you 45 minutes in the instance that your conjecture is incorrect, but you'll still spend 45 minutes verifying it. So it guides you that, all right, out of these 10 ideas, I know these 3 are correct because Mathematica returns a true value. Now I'm going to spend some time trying to prove it. Because as you probably know much better than I will, which is that creating conjectures and having them be false after 7 days is a huge time sink. And then this can hopefully save some of that time. Yeah.
Do you know how resolve works? Like linearity, for example, there's a theorem.
Right.
That all linear inequalities can be solved, and then there's an algorithm that runs that.
Right.
We know how resolve is hard-coded in math. I mean, it's all closed source, of course. But if we knew that, then we could make a resolve tactic in lean.
Yes.
And instead of saying left-hand side, right-hand side, you could just make a lean statement.
Right.
And call the resolve lean tactic, give you the actual proof.
Yeah, I don't know how it works. Yeah, but Vijay has my collaborator has knows someone in Germany who works on similar things, and he said that there's a lot of theorems about how different the exponential function can be proved using an SMT solver, etc. And I think they're using a lot of that in resolve. So there's conjectures about how it's doing that, but it's closed source. Yeah.
So your individual component is well grounded in Mathematica. How do you ensure your decomposition is correct?
Yes. So okay, so let's suppose that's a great question. So if Gemini says, this is how you decompose the domain.
It might miss a piece.
Sorry?
You might decompose in the wrong way where it miss a slice of your space.
Okay, so you're saying what if Gemini returns a decomposition whose union is not the entire domain?
Yeah.
Is that what he's saying?
It just gets it wrong. You actually have to break it up into 5 pieces and not 3.
Yeah.
Right.
then like,
Yeah, that's a fair point. That's a fair point. So I'll give you the different sort of course, Gemini might output a wrong idea. You know, for example, it might not know how to solve an unsolved problem or something like that. Then you can, you know, if Mathematica does not produce a proof, then you can sort of you ask Gemini again that this is wrong, try again. That's really all the best you can do. The second is, even without that, even if Gemini knows how to correctly decompose the domain, it's not always going to give you the exact same output, right? Because you know, these are, you know, like stochastic. So you kind of have to. So I actually found this on social media, which is Greg Brockman, who's like an OpenAI scientist. He has this LLM prompt, which is very reliable in that it makes LLMs output the same kind of answers repeatedly. And you know, you sort of, instead of writing it in English, you sort of, you know, like write it in code format. It's there on our paper. I don't quite remember it right now, but you sort of divide the prompt into multiple blocks, and then you ask the LLM to sort of emphasize. In the prompt itself, it sort of spells things out in a very specific way so that the LLM can give you reliable outputs. So-
JSON code,
Sorry?
you can use JSON code.
It was like JSON code. That's the idea, is that if your input is in code format or similar to code format, then the outputs you get are more reliable than if you just put them in plain English. Yeah. But you're quite right that it might just give you the wrong decomposition, or it might just not know. And then you just have to try again, and then maybe,
Compensation is correct, this is true.
yeah.
But the starting point is wrong, and you have this misbelief that this is right.
Yeah.
You see my point. So you have a wrong decomposition, but each composition is proved by Mathematica.
Yeah, so like, as the decompositions together, they imply the original.
Yes.
Yeah,
Are you
even though they are all
verifying that?
true, your inequality can still be wrong.
So what I'm trying to say is something. So for example, if this domain is decomposed into two parts, A and B, and let's assume A union B is the entire domain, and Mathematica is able to prove that the inequality F is less than or equal to G is true both in A and B, then it does imply that the inequality is true in the entire domain.
Yeah, but that's a strong assumption, right? Because it might just miss another slice in the space.
No, but I'm assuming that the union is equal to the entire domain. So every point, every slice in the domain is included in either A or B.
Mathematica can solve it on A but not B. You send just back, you just change the problem to now I have to prove it for the domain B.
Okay, so for okay,
That's a good.
that's a good point. We haven't implemented that. Yeah. But that's again, it sort of brings us to the broader point, which is that a lot of this is hard coded by me. I can't think of all the possibilities. So a human like me should not be trusted to produce a reliable tool. You should go for just an even larger LLM in the future. So that's the broader point I'm going to come to, which is that we haven't implemented that. And there's a billion ideas out there that we haven't seen. But a large LLM with enough training data and which has seen more than I have will be able to do this more reliably than I ever will. Because a lot of this is just decisions made by me and Vijay, which is sort of hard coding these are the possibilities you should consider. And then if your problem is slightly outside of that range, then, you know, bad luck. So, yes.
So you haven't told us yet how you actually get the proof of the inequality, right? Resolve gives you a true false.
Yes.
And then, so you said it's without human intervention?
Yes.
Okay, I'm so curious.
Oh, I just have one more question. So your filters back true, false, those are the only two options on I don't know?
So false is I don't know.
There is no false, it's true and I don't.
True and I don't know. Yeah.
Okay.
Yeah. So coming so to Lisa's question, yeah. So that's exactly the idea, which is that you don't have humans in the loop. Humans don't have to be involved in any of these processes. Humans just have to put in a conjecture that they have, which is it true that F is less than or equal to G on the real line, or maybe on the interval 0, 1. And then sort of it goes to Gemini, which says you should divide this into 0, 1/2, and then 1/2, 1. Maybe I should make this open. Yeah. And then Mathematica, and then this output, and then a lot of Mathematica code is sent to Mathematica. A lot of this code is sent to Mathematica, which says, okay, I can prove that this is true here as well as here. And because every point in the domain has been included, there's no slice that's left out. So this implies that the inequality is true everywhere in the domain because you've proved it at every point in the domain.
Gemini might say 0 to 1/4. and 3 equal to 1.
I see. So you're saying that Gemini.
There's no way you can verify this is complete.
Okay, so Gemini also gives, so that's a great point. That's a great point. So actually, the way that we've designed the tool is that you get the decomposition of the domain as an output here. So you can check whether the decomposition is equal to the entire domain or not. Yes. So this is something that I haven't sort of shown on the screen for space constraints, but there's sort of one window which tells you the decomposition, another which sort of outputs something like the things Mathematica tried and things like that, and then there's a middle screen which tells you whether it could complete the proof or not. So proof successful or not. Yes. That's a fair point. So what if Gemini cheats and gives you a decomposition that whose union is not the entire domain? But you can verify that that's not true.
Especially in your RL, I think it gives you a shortcut and
Sure. Right.
reward.
Right. Yes. Okay. So API calls are made to a, let me see how I'm doing on time. It's 2 to 3, right? Okay. Maybe I have 5 or 10 minutes. API calls are made to a frontier LLM like Gemini. However, this can be easily modified for, say, ChatGPT Pro or like other powerful models that come out. So the structure is very modular in that if there's a better LLM that comes along, just put in your API key for the better LLM, and now you can get better results. So you're not constrained by the model that we trained or something. You can just keep on using the better tools that come. If you don't like Mathematica, if Lean becomes better, or if some other automated theorem prover becomes better in the future, you can just plug in the API calls for the API key for that instead of Mathematica and use that. So there's every part of this code base is, you can modify it very easily by just inserting a different API key and maybe changing some things about the code. Right. So, as researchers, we would just want to use the most powerful tool out there, and this sort of allows you to do that. Okay, and then API calls are made to Mathematica Cloud, and we were told many mathematicians don't have Mathematica installed. It might be prohibitive, it might be expensive. The universities might not offer them that. So just put everything on the cloud. So I should not have to have Mathematica installed on my computer to use that. It just makes an API call to Mathematica Cloud and then outputs the result. All right, and current math tools created by AI researchers are not always helpful for mathematicians, many of whom might be uncomfortable with programming, like I have experience with alpha geometry. And of course, if you try to use other models, it might, you might have similar installation issues and so on. So, this is something that you can sort of easily use.
Instead of Mathematica in the middle step,
Mhm.
what about using Gödel?
So can Gödel prove return a proof of this? Is that what you're saying? Yeah, you can try that.
Especially by the time you produced it to something that Mathematica can do.
It's possible. My experience with tools like automated theorem provers like this is they're not always good at undergrad math. They're very good at high school math problems. But of course, that's not a permanent problem. It's possible that 6 months down the line, a lot of these tools are much better at undergrad math and graduate math and so on. And that's a fair point.
That you run it on Mathematica, if it says true, then turn around and run it on Gödel.
Right. Right. And in fact, that has the advantage that it returns a proof object, and which can be externally verified. Yeah.
That'll save you the 45 minutes.
Right. There you go. Yes. Yeah.
Does resolve always return true if the statement is true?
If it's able to complete the proof. So SMT solvers like resolve or other things like that are very finicky. So sometimes, for example, if it can complete a proof for A plus B is less than or equal to C, it might not be able to prove that B plus A is less than or equal to C. And this is not just true for Mathematica, this is true for SMT solvers, all kinds of automated theorem provers in general. So they're very, very finicky about the way that things have been phrased. So, so there's, there's that, yeah. So it's not always able to complete a proof, but if you process it correctly, it can produce, proofs for things that'll take you some time to write down. Okay, so maybe I'll just spend, okay, so what is a research level question? For example, this is like an unanswered question on math overflow, for example. So we are able to solve things like that. Of course, we are hard coding the method to solve questions like this. So if you take a problem that's very different from this, can our tool solve it? I don't know, right? We're still using an LLM, but a lot of the tactics that we're using to simplify this expression are hard coded by us. So that's the limitation. And that's a very natural reason that things don't generalize, that these tools don't generalize to problems that are out of distribution, is because you can't think of all possibilities. So there's always going to be problems that you can slightly tweak this problem, and then our tool is not going to be able to solve that.
But you want to know if this is true or false.
Yes.
You haven't actually given the proof.
Yeah. So yeah, all that we know is the way that the domain was decomposed, or the way that this series was split into 3 or 4 things, etc. And then that whether Mathematica was able to complete a proof of this estimate for each part. You don't know the proof yet. That's correct. Yeah. All right. And why did we use the resolve function? Is because first we tried everything else, and none of it worked. Right. So for example, Sage, Z3, Metatarsky, which are some very powerful SMT solvers, they're not even able to prove that if X is less than Y, then this implies that e to the X is less than e to the Y.
They
Yeah.
know that he's monotonic.
They do know it's monotonic. But they should know it's monotonic.
Not true if they're matrices. That's what it.
Right. Right. So maybe they're thinking of it in, they're just very underpowered. They can't deal with transcendental functions in particular. Like Metatarsky is supposed to deal with transcendental functions. That's the reason why it was defined, but it was just not able to implement it. So we tried everything else before we tried resolve. And, and resolve works the best for our purposes because it can actually deal with some complicated things like this and, proving this and so on. Okay, we've tested this tool on hundreds of problems drawn from research mathematics. What does research mathematics mean? Problems in Math Overflow, problems on online forums. Of course, hundreds is a very small number. So it's quite possible that you can tweak a certain question and then our tool will not be able to complete the proof for that. So that's sort of a feature or a bug, however you see it, which is that any tool that is not a ginormous LLM is going to have ways of sort of you're going to be able to ask questions that are only slightly different from what it can solve, and it's going to fall flat on those, like alpha geometry. Sure.
He's running it.
Okay. It's also there in the left panel, this is one of those bucket questions that you put. You can just click on that and yeah. Yeah. Okay, the drawbacks are that no proof term is produced and scope is restricted to inequalities as of now. But the idea is very general in that you take something that's complicated and you break it down into smaller pieces that are easier. Automated theorem provers can do easy things. They can't always do more difficult things. So you should be able to use this for all kinds of problems and not just inequalities. It's just that for humans, as for AI tools, if you take something that's complicated and break it down, automated theorem provers can pick up the slack and complete goals for those easy things. Yes.
So if I can produce a proof, I don't know whether this is correct or not. And you have some software to just verify.
So if Mathematica says yes, true, then it has produced a proof for that under the hood that uses only first order logic. So axiomatically, that proof is correct.
So I don't want it to write a proof. I give it a proof.
Oh, so you want just a verifier?
Just verify.
Well, Lean is one way to do that.
Okay.
So if you write a proof in Lean and Lean verifies that it's correct, then then it's correct.
That means you can just let LM to propose a Lean proof of your any inequality.
Yes.
And let Lean execute it. If it's true, then you get both correct and the proof.
That's correct. More difficult than it sounds. So using LLMs to write Lean proofs is something that a lot of people are trying. I try it every day. I teach a Lean course. LLMs are getting better, but even for problems that are proofs that LLMs know very well, they don't always output the right Lean proof. And for questions like this, which it hasn't seen before, for example, something as complicated as this, it's almost certainly going to write a wrong Lean proof if it's able to produce a proof at all.
So one thing you can do is use your decomposition and prompt it to write Lean code in a modularized way.
Sure.
And then just verify this Lean.
Yes, that's fair. So yeah, that's correct. You can definitely do that. Currently using Mathematica code is more reliable because LLMs are not very, you can try it yourself. Like I try using LLMs to write Lean code all the time. They're great. They're not always very good at writing correct Lean code if it's very long. And even if there's like a small error in that, it's not going to compile And then, of course, you can sort of reprocess that and run it in loop, but that's an entirely different problem from using Mathematica, which is sort of more reliable in that, using these tools, if it has a lot of sort of tactics under the hood that it can use to complete a proof. So the LLM is not producing the proof here. It's Mathematica that's producing the proof. So that's sort of, it's a different sort of way to look at it. Yeah. All right, and we acknowledge Terence's help for stress testing this tool and providing the initial idea of creating the website. And we also acknowledge help from Swarat, Ayman, Amit, Ayush, and George. Right, thank you.
Yeah, I